Hi folks, we're going to take a look at page 234, number 16. So here they ask us what values of m does this equation given here satisfy this other equation. Okay, now first thing I want to point out is that there's a typo in the textbook because here y is given as a function of t, but the derivatives were given as derivatives with respect to x. So that really doesn't make much sense, because if I were then to take derivative with respect to x, all of these things would just be constants. So we'd just get 0. So a little typo. So either I needed to change the variable of differentiation to t, otherwise I would just have to change this variable as x. Okay, I chose to stick with t because this type of equation often models, some sort of exponential behavior, and more often than not, the independent variable there is time. So I decided to leave it as t. Okay, so this equation here is actually an example of what's called a differential equation, because the equation doesn't just involve the function, but also involves derivatives of the function, and these, become exceedingly important later on. Okay, so let's actually solve the problem. So in here, I'm going to need the derivative and second derivative. So on the side, let's calculate those. Okay, so we've got the derivative. Now notice here when I write y prime, I'm assuming that I'm taking the derivative with respect to t, because that's the variable used in the equation. Okay, so a is just a constant. So take that out. Now I have to take the derivative of e to the mt. So again, this mt will be like my u. So derivative of e to the u is just e to the u. So e to the mt, and now I have to take the derivative of mt. M is just a constant. Derivative of t is equal to 1, so that's just m. Okay, so in the end I have am e to the mt, and now the second derivative looks like it's going to be pretty similar, because again now a times m, that's just a pair of constants multiplied, and again the derivative of e to the mt is just e to the mt times m. So when I simplify, I have am squared e to the mt. Okay, so now let's input all these things into the equation we have to solve. So the second derivative is am squared e to the mt. The first derivative is a times m times e to the mt minus 6 times y, and y is just a e to the mt. Okay, equals 0. Okay, and I hope we're starting to see this trick that we're using very often, that when you have to simplify an expression that has all these common terms, is to just factor them out. So here we see that there's a common factor of a in each of those terms, and there's also a common factor of e to the mt. So you see this a lot with exponential functions, since the derivative will bring about the same function. So let's see what we're left with. We're left with an m squared from the first term, plus m from the second term, and a minus 6 from the third term. Okay, and now let's keep going. So we've got a e to the mt, and this luckily is easily factorable, so this will be m plus 3, m minus 2. Okay, so now I've got the product of 4 expressions, and so, well, a is just some constant that doesn't depend on m, so that's not going to come into play. So we've got this expression here, but it's an exponential one. So there's no value of m, which is going to make this first factor 0. So e to the mt is never equal to 0. So that's not going to generate any answers. But here, if we have m equals to -3 or m equals to 2, that'll make that expression equal to 0. And so there's our answer. Okay, so just a quick recap. Here, you just have to input all the components of the equation, which involve both the function, the first derivative, and the second derivative, and then use common factoring to simplify the expression.